Welcome back. These are the exercises for section 1.9. I've got 4 of them picked out, and I'm excited to get through them quickly so we can move on to chapter 2 where things start to get really interesting. So, first off, number 5 here says, basically all the exercises here say, use algebra to simplify the expression and find the limit. Now, I've picked out some hard ones for exercises, and that's because I want to make sure that you have a chance to see all the different tricks that you might need, including one particular tricky one. So make sure that you try these, but then you watch how I do them, and you learn these tricks. Not all of them are in the lecture video. This one is pretty simple, though. We look at this thing, and we want to take the limit as t goes to 0. If we just try to plug in 0, we get 0 over 0. So that means we don't know what to do yet. Let's just do some arithmetic. Let's try to factor and see if anything cancels. The numerator factors into t squared, because both of the terms have a t squared. And then what's left is t squared plus 1. In the denominator, both of those terms have a t squared as well, leaving me with a 2t minus 9. So we want to cancel the t squared. We can do that as long as we don't try to plug in t equals 0, and thankfully the limit that we're taking is as t goes to 0. So that means we'll never actually try to plug in 0 itself, so we can cancel. That means what we've got is now the limit as t goes to 0 of t squared plus 1 over 2t minus 9. And actually this is very easy because the numerator and the denominator, both of them are not 0 when I try to plug in t equals 0. These are polynomials. So if I use that nice property of limits where I write this as the limit of the top divided by the limit of the bottom, let me add parentheses here so it's totally unambiguous. One of our properties of limits, I think number 4 maybe, says that these are equal. This is the limit of the fraction versus the fraction of the limits. These are equal as long as this is not 0 and both of these limits exist. And they do exist because they're both polynomials. So I can just plug in 0 and I get 1 for the top and negative 9 for the bottom. So we could just write this a little nicer as negative 1/9. And that's our answer. That's our limit. So we factored, and then we canceled, and then what was left still looked complicated at first, but actually nothing goes wrong here. I'm allowed to plug in 0. This function is not continuous everywhere. It is possible to make that denominator 0, but it is continuous at t equals 0, the point we care about. So you plug it in, and you get negative 1/9. Okay, not so bad, I hope. Moving on to number 21. Now this one looks different than any of the ones we saw in the lecture because of this square root. So if you just saw this problem and tried to solve it without knowing the trick, you wouldn't be able to do it probably. Maybe you would, but it would be hard. I'm going to show you the trick, and this is just a trick you have to remember for when you're dealing with roots. The problem here is if you try to plug in h equals 0, the denominator is 0, the top is the square root of 9 minus 3. That's 3. I mean, it's 3 minus 3 is 0. So we can't just plug it in. But on the other hand, how do you factor that? How do we try to factor an h out of that? We don't really know how to factor square roots. So here's the trick. Whenever you see something with a square root, let's say you have square root of something a plus something outside b. Here the a is like my 9 plus h, and the b is like my minus 3. If you want to make that disappear, the trick is that you multiply by the square root of a minus b. The key is that you switch the sign here. That's going to make the square root vanish because when you multiply these out, now this is really tricky, but when you multiply these out, you have the square root of a times the square root of a. That's just a. Then you have a plus b times root a. Then you have a minus b times root a. And then you have a minus b squared. So these cancel because they're the same, and we're just left with a minus b squared. Okay, so this is a really important trick to get rid of a square root. you multiply by, sometimes this is called the conjugate, although you don't need to remember that word, the same thing except the plus sign turns into a minus sign. And if this one had a minus sign, you would do a plus sign. Okay, so we're going to do that to try to get rid of the square root. We're going to take this limit. Well, for now, we'll just take what's inside. Now, if I want to get rid of the square root, according to this kind of scheme, this trick I laid out here, we should multiply by, so let's make some parentheses, square root of 9 plus h plus 3. Okay, hopefully at this point, though, some alarm bells are going off in your head. We can't just take this and multiply it by something. We're changing the value, right? You can't just multiply by whatever. That changes your function. So since this is a fraction, what we're going to do is multiply by the same thing on the top and bottom. Now, we'll work this out, but because of this whole trick over here, what that's going to do is it's going to get rid of the root in the denominator. And you might say, well, wait a minute. Now I'm just adding a root in the denominator. How is that helpful at all? The reason this is helpful is that plugging h equals 0 into my original root gives me 0. So I'm stuck with 0 over 0, and that's not good. But plugging h equals 0 into this conjugate version here, that doesn't give me 0 anymore. That gives me 6. And I don't care if I have some extra 6's floating around. I know how to deal with that. It's when I have zeros that gets me in trouble. So even though this looks at first like we're just moving the root around, this is going to be helpful. So what do we get when we multiply this out? These two multiply out to give me 9 plus h. Then I have the inner term that cancels with the outer term, just like these two here. And then I have minus 3 times plus 3 is minus 9. My denominator is h times this extra term. So this is going to turn out nice because we've got 9 minus 9, and then the top is h, and we've got an h in the bottom. So actually that cancels too. If that's 2 steps in 1. If you don't see that, just write them out one at a time, and I'm sure you will. That leaves us with 1 over the square root of 9 plus h plus 3. Now, if this was just giving me 0 in the denominator, then my problem is not really any better. Except, like I said, this is not the original one. This is the conjugate. So the limit as h goes to 0 of this thing is easy because this inside is continuous at 0. There's no problems. I'm allowed to take the square root of 9, and then the denominator is not 0. That's fine. So I can just plug in 0. When I plug in 0, I get 1 over 3 plus 3 is 1 over 6. So the whole trick here, which you would not have known probably unless you saw the trick, is to multiply by this conjugate. That's just a trick that you need to keep in your head whenever you're trying to cancel out something with a root like that. Okay, that was our second of 4 problems. Moving on to number 3. This is number 31. Same question, use algebra to evaluate the limit. This one is not too complicated, actually. This is a very easy thing to understand, except for the way it's expressed looks very confusing. So what we're going to do is simplify this to something that's more clear, and then it will be really obvious what the limit is. The problem here is that we've got 2 exponentials on the top and bottom. The bottom is 3, the top has a base of 2, and so you might think, well, 3 is going to grow bigger, so it must go to 0. But it's trickier than that because we've got this 3x plus 2 and this x plus 3. So what I want to try to do is untangle the numerator and the denominator. So we've got something to the x, just a very clear exponential, times or plus or whatever, all this extra stuff. So we need to use our rules of exponents here. Let's start with 2 to the 3x plus 2. What I'd like to do is end up with just a number to the x with everything else around it, not in that exponential part. So our rules of exponents say that we can simplify this to 2 to the 3x times 2 to the 2. Addition in the power becomes multiplication outside. That's one of our fundamental rules. Now, of course, 2 squared is 4. So let's write this as 4 times 2 to the 3x. But this is still not quite simple enough. I want just a number to the x. So now we use the rule that says if I have a to the b times c, I can think about this as a to the b first, then to the c. This is one of the ones that always looks weird to me, but it says that multiplication inside the exponent is like repeated exponentiation. First the first power, and then the second one. So that means that 2 to the 3x can be written as 2 to the 3 to the x, which is just 4 times 8 to the x. Okay, that's our numerator. Let's do the same thing with the denominator. This one's a little bit easier. 3 to the x plus 3. First step, make it 3 to the x times 3 to the 3. 3 cubed, that's 3 times 3 is 9, times another 3 is 27. And now we already only had a single x in there, so we don't need the other step that we needed here. Okay, so that's going to help us now untangling what those functions were doing. We want the limit as x goes to infinity of, so now let's write what we discovered these actually are. 4 times 8 to the x over 27 times 3 to the x. And let's fix that infinity, which got a little weird. Infinity is a kind of hard symbol to write. Let's rewrite this just a little bit more. The point that I want to make is that this is actually just one big exponential function. We wrote it as the ratio of two exponentials, but you can actually write it as, so some big parentheses here, 4 over 27. Okay, so pulling out those constant multiples, that's like the p0 in the exponential formula. And then we have 8 to the x over 3 to the x. But again, we have a rule of exponentiation that says a to the x over b to the x can be written as a over b to the x. And hopefully that makes sense, because that's like saying you have a multiplied by itself x times divided by b multiplied by itself x times. Well, you could just say that that's a over b, that whole thing, x times. So if you were to think about that as repeated powers, a repeated multiplication, that should make sense. So that means I can make this 8/3 to the x. Okay, so this is just a really basic exponential function. This is a p0 times a to the x, where p0 is that constant, and a, that's our exponential growth rate. But is this growth or decay? 8/3, well, let's see, 3/3 is 1, 6/3 is 2, so this is like 2 2/3, like 2.67. So this is an exponential growth. We've got a positive number here times a number bigger than 1 to the x, and so as I go to infinity, we know exactly what should happen. We have a function that looks like that. We know what this intercept is, but we don't care for this problem. As we go to infinity, as x goes to infinity, the function goes to infinity, just because we've discovered that it's exponential growth. So the limit equals positive infinity. Okay, we've got one more to do. And this one is also a little bit tricky. This is using a technique that the book talks about in the lecture, although I didn't mention it in the lecture video because I wanted to save it for this one. This is why it's important to always watch the exercise videos. You should consider them as part of the lecture. Even if they're not in that video, it's part of the normal 50 minutes of lecture that you would see if we had an in-person class. So what we're going to do is find a limit, except we've got this extra wrinkle that they're going to tell us how to do a change of variable to solve for it. Now, this is a little bit of a tricky thing. You could solve this limit without any change of variable, but you'd have to do some factoring with exponential functions. And in order to do that, you have to have a really good understanding of the rules of exponents and how they factor. And that can be hard to do. So the trick that they're introducing is that if we turn e to the x into a new variable t, then the factoring will become obvious. We're basically turning our exponentials temporarily into polynomials, and we know how to factor polynomials. So we're turning the problem from a way that's harder to think about into a way that's easier to think about. So we're going to do this change of variable. We're going to turn e to the x into t. So let's think about that. That means e to the x is going to become t. What about e to the 2x? Now, it would be very tempting at first to think that this is just going to be 2t. But we have to remember that e to the 2x, another way to write that would be e to the x times 2. That looks a little bit weird, but I'm leading into that same property from before, where this is e to the x squared. So that's our, I'll write it once again, that's our a to the b times c equals a to the b to the c. Same rule once again. So this goes to, if this part here is t, this goes to t squared. By the exact same rule, e to the 3x goes to t cubed. Not 3t, but t cubed. Good. Now there's one other thing which would be really easy to forget. This limit is as x goes to 0. X goes to 0 is not the same as t goes to 0. X goes to 0, that's our old variable. If we're going to change our variable, we need to make sure to adjust this part as well. So let's think about our substitution. As x goes to 0, what does e to the x go to? Well, e to the x is a nice continuous function. So in order to know what it goes to as 0, we can just plug in 0. That's e to the 0 equals 1. So when x equals 0, that means t is 1. And really, we could have seen that simpler by saying, by plugging in e to the 0 up here, e to the 0 is 1. So when x is 0, t is 1. So this is probably the most common mistake with a question like this. If you're going to make a change of variable, you have to make sure you change your limit variable too. That means our transformed version of this problem is that it's the limit as t goes to 1, not 0, but 1, of, now we make all our substitutions, e to the 3x, that's t cubed, minus e to the 2x, that's t squared, over e to the x, that's t, minus 1. Now, one way that you maybe could have caught your mistake if you forgot to do the change of variable is that up here, if you plug in x equals 0, you have a problem. That's the whole point of the limit, is you can't just plug in x equals 0, because you get e to the 0 minus e to the 0, that's 0, over e to the 0 minus 1, that's 0. So you get 0 over 0. If you forgot to change your limit and you said t equals 0, you wouldn't have a problem here. You'd have 0 over negative 1. That's 0. That's easy enough. So if you forgot to change your limit, you would have had something that that's not easy turning into something where you can just plug it in. And that wouldn't make sense. Plugging in 0 gives you a problem here, and therefore plugging in your new limit should give you a problem here. And if you got it right, and you got 1, then it does. Because now you have 1 minus 1 over 1 minus 1. And that's 0 over 0. But since we've turned it into polynomials, we can use all of the things we know about polynomials, like factoring, to solve. So what we'll do is we'll factor the numerator. Both terms have a t squared. And when we factor it out, we're left with a t minus 1. And thankfully, we can cancel these, because even though they don't exist at 1, we're taking the limit at 1, which means we don't care about what happens at 1. So we're left with just the limit as t goes to 1 of t squared. And this is easy, because this is a polynomial, so its limit you can find by just plugging it in. When you plug in 1 to this, you get 1. So there we go. This is our answer. This is the limit here. It would have been possible to figure that out without doing a change of variable, but you really have to think about, how can I factor something like this? And let me just show you, just in case you're curious. You have to really remember your rules of exponents, but what they say is that you can factor an e to the 2x out of both of these, and what's left is e to the x minus 1. Now, how can you check that? Well, multiply it back out. E to the 2x times e to the x. E to the 2x times e to the x. The way this works, it's the same as the rule we saw before, but in reverse. This is e to the 2x plus x, which is e to the 3x. So that's good. So this is good. and then e to the 2x minus 1 gives us this term. So this is how you would have factored it, and this would have canceled with the denominator. Then you would have plugged in 0 to this and got 1. So maybe you're really good with those rules of exponents, and that seems easier to you. For me, especially when they give you the change of variable, I think this way is a little bit more straightforward because we're just dealing with polynomials. Okay, so that was the 4 exercises. This concludes our work in Chapter 1. We'll start in soon on Section 2.1. That's all for today.